Now we're going to talk about intermediate value theorem for continuous function. If f is a continuous function on the closed interval ab, and if you have two numbers x on the, for example, f of a times f of b less than 0, what does it mean? You have a point here, for example, and you have a point, for example, here you have a point x. Let us say this is a, okay, and this is b. If f of a1 is negative and f of b is positive, if the function is continuous and it means the product is negative, certainly going from minus to positive, it will cut the x-axis and at least one point. So we say there exists a point alpha, like this alpha here on the intersection, so that f of alpha equal to 0. And if it's strictly monotonic, increasing or decreasing, if you have 2 points, f of a is positive, like here, f of b is negative, the product f of a times f of b negative, going from positive to negative, certainly it will cut the x-axis because it's monotonic in one and only one point alpha, such that f of alpha equal to 0. So here in the problem, show that there exists a root such that the equation, I told you I want it between 1 and 2, such that x cubed minus x minus 2 equal to 0. X cubed minus x minus 1, f of x, for example, which is equal x cubed minus x minus 1, is a continuous function. So if you do f of 1, you're going to get minus 1. This is a negative value. So if x equal to 1, you have minus 1. And if you do f of 2, you have 5. F of 2, you have a 5. Certainly, because it's continuous, going from negative to positive, by this theorem, we can say there exists at least one real number between 1 and 2 such that f of alpha equal to 0. To have only one and only one point, the function must be strictly increasing or decreasing. So either f prime of x is always positive or always negative. Let us do it. 3x squared. Now we have 3x squared, so I have only 1 point since this is always increasing. But since I have minus 1, it can be going up or going down, or f prime of x can be positive or negative. So here I have at least 1 point. Now prove that this equation has a solution for f of alpha equal to 2. I want to have here not at 0, I want it at alpha equal, at y equal to 2, I have a root. This function will intersect it at alpha equal to 2. For example, you have like this, it will cut it at elevation 2. So here my aim is to find a point whose value is less than 2, less down, and the value whose y is bigger than 2. So going from, because 2 is between these two numbers and is continuous, it will cut it. So I want it between 0 and 2. So we do f of 0. So if you do it, you have minus 3.5. I'm comparing it to 2, to the line 2. It is less than 2. It's below 2. And if you do, so f of 0 is minus 3.5 is down. And you have f of 2, it is 3. So if you take 2, this is 0. If you take 2, you have a 3. So because it is a continuous function, so it will cut going from a value below 2 to a value more than 2. It will cut it in a point, at least in 1 point. Why? Because 2 is between this 2 is between f of 0, which is minus 3.5, and f of 2, which is 3. Explain why the equation has one solution, f of x equal to 0. I didn't give you the interval I want to discuss. You can pick by yourself. So the first easiest one, I pick 0. If you do f of 0, it's minus 2. It is less than 0. I'm comparing to 0. I want a value less than this number, a value bigger than this number. Here you had 2, a value less than this number in y, and a value bigger in y of that number. So now I want 1 to be positive. Let us check 1. So 1 plus 2, it's positive. So I have f of 0 times f of 1. It's a negative value because minus 2 times 1. Then there exists at least one real number alpha between 0 and 1 such that f of alpha equal to 0. Now we took the derivative last year. What does it mean? When the function is increasing here, the derivative is positive. at maximum or minimum at vertices it is 0. Here positive, going up. Here derivative f prime of a equal to 0. Here derivative is less than 0, decreasing. Here f prime of b equal to 0. Here, from here till here, f prime of x going up bigger than 0. F prime of c, because it's a maximum, equal to 0. And then derivative here less than 0. So when the function is increasing, derivative is positive. When the function is decreasing, the derivative is negative. And maximum and at vertices, derivative equal to 0. So by limit, what is the how do we find the using limit the derivative? We know that suppose you have 2 points A and B. Suppose I want to find the derivative at the point A. So always the derivative is nothing else than the tangent to the curve at f of x. Why? Because if you want to know if the function is increasing, you can pick 2 points A and B. If the ratio f of xb, if the going up, if you have 2 points here, A, x of A, as in picture, and here you have x of b. If y of b is bigger than y of a, like here, so the ratio is positive, positive over positive. So this means the function is increasing. If you have decreasing, if you have, for example, here a, here b, so here a is smaller than b, as you can see. If you have decreasing, here f of xa, this is the image of b, is bigger than f of xb, and here just the opposite. So if this ratio, which is the slope, is negative, it means decreasing. So that's why we say definition of the derivative, always we say, so it's the study of the slope, and the derivative is what? As long, for example, as b becomes near a, from that side or from that side, okay, if the limit as x of b tends to x of a from left or from right is positive, so derivative is bigger than 0. Negative, derivative less than 0. So that's why we say, what is the derivative? We took it in last year. It is to a function. The derivative at a point, for example, small a, is nothing else than the tangent to the curve at that point. And always the derivative by definition, for example, is f prime of a is limit as x tends to a plus, for example here from the right, of f of x minus f of a over x minus a, which is here f of x minus f of a over x minus a is the slope. If the slope is positive, it's increasing, but when x tends to a, this slope that you have it here will become tangent. So that's why the derivative is the tangent at the function, equal limit as x tends to a minus of f of x minus f of a over x minus x of a. So if left equal right, we say that the function is derivable at x equal to a. You took this last year. So as a summary, we said f of x is derivable at x equal to a if f prime of a equal limit as x tends to a f of x minus f of a over x minus a, right and left. هلا note, if f of x is derivable at x of a 100%, it's continuous. If not there, if it is continuous, it doesn't mean it is derivable. Here, this is the proof why if it is derivable, it is continuous. How do we prove it? If it's derivable, as we said, we have the property. We need to show it is continuous. Limit as x tends to, we're going to do it in the coming video because I don't have enough time here.